Hello everybody. So today we're going to derive the one-dimensional heat diffusion equation for a material of constant thermal diffusivity. So to start with this problem, we're going to establish that there's a bar here that we're solving for, so that'll help explain. And additionally, we're going to divide this up into little segments, and we're going to specifically focus on this shaded region. All right. And so additionally, we're going to establish that this length is delta x. Is our total length of this small brick. So the heat flow going in is going to be represented by Q left, which is going into the brick, and then the heat flow leaving is going to be established by Q right, which is heat flow leaving. I'm going to establish what these means. We're going to first go with Q left, which is equal to the thermal conductivity, represented by negative K, the area of the equation, and then the derivative of temperature with respect to position. So in this case, it will be x is going to the left. Additionally, with the right one, it's going to be the exact same equation with the thermal conductivity, negative thermal conductivity, area, and then the temperature, the derivative of the temperature with respect to position at x equals to the right. The last equation we're going to need to really get this going is the energy equation, which can be established with Q is equal to the temperature with respect to time. So that will be represented by dt over d lowercase dt. And then we're going to have heat capacity, volume, and the density as well. So we have the derivative of the temperature with respect to time, the heat capacity, the volume, and the density. So to establish our one-dimensional equation, we're going to set these equal to each other over here, as Q will be equal to Q left plus Q right. Now, for the sake of this, we're going to establish that everything is in absolute values here, so that way we don't have to worry about the negatives and which way the heat is flowing the entire time. So now putting everything in, we have our temperature gradient with respect to time, our heat capacity, our volume, and our density. It's equal to our thermal conductivity, area, and then our temperature gradient with respect to position this time. And then the same thing for the right side as well, with our thermal conductivity, our temperature gradient with respect to position. So now we want to start canceling some stuff out and make some stuff a little bit cleaner. So our volume is actually equal to our area times our length. So delta x times area. Now if you notice here, these also have areas that we can separate across, and we can get rid of that entirely. So we have our temperature gradient with respect to time, heat capacity, our delta x, and our density with our thermal conductivity, dt tx with respect to position. And then the same thing for the right. Now, if you remember from our previous lesson, our thermal diffusivity is equal to the thermal conductivity with the density over the heat capacity. So, knowing this, we can actually simplify this even further, getting rid of this and isolating that temperature gradient with respect to time. So we'll go down here. So we're almost done. And if you notice right here, the delta x is actually positioned between the x to the left, or the q to the left and the q to the right. So knowing this, that this is just a position over the derivative over the position, we can actually just assume that this is the second derivative, which would give us our final equation of our heat diffusion equation with respect to time. That's our final equation for our heat diffusion equation for material constant thermal diffusivity. Thank you very much. Hello everyone. So today we're going to be going over stimulating the response of a uniform rod through forward or explicit finite differencing of the heat diffusion equation. And we're going to be showing a critical value in this, the ratio of thermal diffusivity, so that the square of the spotted differences are numerically unstable. So first we're going to start off with some basic equations that are key in this. So the situation that we were talking about, we're going to have a long like bar, and we're going to separate that into three parts. Or we have Ti minus 1, Ti, and Ti plus 1. So from that equation, as we've already gone over before, we have Ti plus 1 minus Ti, I've got an n up there, all over delta T, and then equals the thermal diffusivity, and then in quotations that Ti plus 1, so this value again, the temperature of that block, the nth, and then minus 2 Ti, so and then times double of that temperature, that middle block, and then plus Ti minus 1, and then all over delta x squared. So now we want to separate that Ti plus 1, where we get the following equation. So that's the equation we're going to be working with in this Excel file. So this is very important to what we're about to be doing. Hello everyone. So today we're going to be showing the limitations of Excel through stimulating the response of a uniform rod through the forward or explicit finite differencing of a heat diffusion equation. So we're going to show that there's a critical value in this Excel, and so we're going to use that problem of the metal bar with two opposite end temperatures and our initial temperature as well. So our R value, we're going to represent that as 0.3. Our T initial, that's our temperature when time is equal to 0, we will say is 20 degrees. Our temperature to the left, we're going to say that's 50 degrees. And then our temperature to the right is going to be 80 degrees. First thing we want to do is we want to set up a counter right here. We'll make that a series, so it goes all the way down. So we got it going all the way down to 1,000. So now we have our temperature to the left, which is 50 degrees. And this will go all the way down to that 1,000 value. Now we're going to have our temperature in the middle, which we will assume is 20. And then I am going to do 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm going to do 20 right here. And then move this. Our temperature to the right is 80 degrees. This will get dragged down all the way down. I think that's in line, but let me make sure. Yeah, okay. Make sure. All right, so now we're going to do our heat diffusion equation, which, if you guys remember correctly, was our temperature initial plus we have our R value times this value right here minus 2 times that initial value. Nope, don't want to do that. Their initial value plus we got temperature to the right minus 2 times temperature to the left. That's why I didn't set it up. Okay. Let's see, 9. And then plus temperature to the left. And then we also just want to make sure that this is constant throughout the process. Multiplication there. So our desired value, to check before, is 29. So now we can drag this over. And we should get all these values. So I can drag this all the way down. Oh, we're getting 25 though. Oh, that's why. Okay. Sorry, that's being weird. Maybe if I just drag all these down. Sorry, this might take a little bit. All right, so now, after that little tedious process, so we can kind of see that we have, we can see the temperatures at each of these points on our bar at different times. And it looks pretty good right now. at the 0.3 interval. So, we're kind of getting this step right here at about, what is that, like 1.5-ish, somewhere in there. So, to check on these, see where we're having issues or limitations in Excel at least, it was 0.8. We'll do that one, for example. We're getting negatives. There's no way it could be negative. Let's take it down. 0.6. Still getting these negative numbers. You don't even have to scroll down. It can't be negative 81 degrees. Let's do 0.4. We're not getting negative numbers anymore. All these numbers look pretty consistent. They look good. So let's do 0.51. It looks good, looks good. Still looks good. But right here, 33 and 82. It doesn't make any sense off one interval. But if we did 0.4999, you don't get those anymore. It's in order. You don't see like 80s randomly. So our limit here, if you haven't figured it out, is 0.5 is our limit where we start having issues. Let's see if I can try to find any, but I don't think I should on 0.5. I don't see any. The 0.5 is our limit. So even so, let's do that one right there and see if we can find any issues. I don't know if Excel will register it, but the point being is 0.5 is our limit to where we have issues here and where our limitations. And the main cause of this is because of round off in our values. So Excel will round up and it'll end up causing these weird numbers to show itself when we do our calculations here. So that is why there's some differencing and why these numerical calculations are unstable. Thank you very much.